Download this code from codegive.com, link in the description below. Directx and Hyper-V, exploring the new attack surface. This tutorial delves into a relatively unexplored and potentially concerning attack surface, the interaction between Directx, specifically Direct3D, and Hyper-V's remotefx virtual GPU, vgpu. It's a complex topic, so we'll break it down step by step, covering 1. Fundamentals, Directx, Direct3D, and Hyper-V vgpu. 2. How Directx works in a Hyper-V environment. 3. The potential attack surface, remotefx code execution. 4. Proof of concept, shader injection and exploitation, theoretical. 5. Mitigation strategies. 6. Ethical considerations. 7. Conclusion and further research. Disclaimer *: This tutorial is for educational and research purposes only. The techniques described could potentially be used for malicious purposes. Do not use this information to compromise systems you do not own or have explicit permission to test. We are exploring theoretical vulnerabilities, not providing ready-made exploits. Security is a continuously evolving field, and specific vulnerabilities may already be patched or have mitigations in place. 1. Fundamentals, Directx, Direct3D, and Hyper-V vgpu. Directx a collection of application programming interfaces, APIs, from Microsoft for handling tasks related to multimedia, especially game programming and video, on Microsoft platforms. Key components include Direct3D, for graphics, directsound, for audio, and directinput, for input devices. Direct3D, D3D the primary API within Directx for rendering 3D graphics. It provides a low-level interface to the graphics processing unit, GPU. Applications use D3D to define the geometry, textures, and lighting of objects in a scene, and D3D translates these instructions into commands that the GPU can execute. Hyper-V Microsoft's hardware virtualization product. It allows you to run multiple operating systems concurrently as virtual machines, VMS, on a single physical host machine. remotefx vgpu a feature of Hyper-V that enables hardware acceleration of graphics in VMS. Instead of the VM relying on a purely software-based rendering solution, remotefx vgpu allows it to share the physical GPU on the host machine. This provides a significant performance boost for graphics-intensive applications running in the VM. How it works: remotefx vgpu creates a virtualized GPU inside the VM. The VM's operating system and applications interact with this virtualized GPU using the standard Directx APIs, like Direct3D. The remotefx vgpu driver, running within the VM, translates these Directx commands and data into a format suitable for transmission to the Hyper-V host. On the host, a component called remotefx vgpu then translates those instructions into GPU-specific commands, and then directs the real GPU hardware to process the commands. 2. How Directx works in a Hyper-V environment. In a typical Hyper-V setup with remotefx vgpu enabled, the following process occurs when a Directx application inside the VM wants to render something. One application calls D3D*. The application in the VM makes a call to a D3D API function, example drawIndexed primitive. 2. D3D translates to commands*. The D3D runtime in the VM translates the high-level API call into a stream of GPU commands and data, vertex buffers, textures, shaders, etc. 3. remotefx driver*. The remotefx vgpu driver running inside the VM intercepts these D3D commands. For serialization *, the driver serializes the D3D commands and data into a format suitable for transport to the host. This might involve compressing data, converting data formats, or encapsulating the commands in a proprietary protocol. 5. Transmission *, the serialized data is transmitted over a Hyper-V virtual bus, VM bus, to the host machine. VM bus is a high-speed communication channel designed for inter-VM and VM host communication. 6. Host-side processing *, on the host, the remotefx vgpu component receives the serialized data. 7. Deserialization *, the host-side component deserializes the data, reconstructing the D3D commands and data. 8. GPU driver communication *, the remotefx vgpu host-side component interacts with the physical GPU driver to execute the D3D commands. This interaction happens through the native device driver interface, DDI, of the GPU. The host system uses the actual physical GPU driver to talk to the GPU. 9. Rendering *, the GPU executes the commands, rendering the scene. 10. Frame buffer transfer, optional. The rendered image might need to be transferred back to the VM's virtual display for presentation. This transfer can also occur over the VM bus. 3. The potential attack surface, remotefx code execution. The complexity of the remotefx vGPU architecture introduces several potential attack surfaces. Serialization/deserialization bugs *, errors in the serialization or deserialization process could lead to buffer overflows, format string vulnerabilities, or other memory corruption issues. A carefully crafted D3D command stream sent from the VM could exploit these bugs to execute arbitrary code on the host. *VM bus protocol bugs *, vulnerabilities in the VM bus communication protocol itself could be exploited to inject malicious data into the data stream, potentially leading to code execution on the host. *remotefx vGPU driver bugs, host bugs in the host-side remotefx vGPU driver could allow an attacker to gain control of the driver and, potentially, the entire host system. This could arise from poor handling of malformed D3D commands or data. *shader injection *, this is a significant theoretical attack vector. Attackers can potentially craft malicious shaders which are then executed by the GPU on the host. Shaders have access to memory and resources, and if a vulnerability exists within how the remotefx implementation handles these shaders, arbitrary code execution could result. The key attack surface lies in the translation between the VM's Directx commands and the host's GPU driver instructions. This translation process, handled by the remotefx vGPU components, is where vulnerabilities are most likely to be found. 4. Proof of concept, shader injection and exploitation, theoretical. Let's focus on the shader injection attack vector to illustrate the concept, along with theoretical, and very simplified, code examples. This is a highly complex area, and real-world exploitation would require significant reverse engineering and debugging skills. Overview Shaders are small programs that run on the GPU. They are written in a language like HLSL, High-Level Shading Language, or GLSL. Shaders are used to perform calculations on each vertex or pixel of a 3D scene. If an attacker can inject malicious shader code into the rendering pipeline, they might be able to execute arbitrary code on the GPU, which, in the context of remotefx, means on the host's GPU. Steps, theoretical. 1. Identify a target. The attacker needs to identify a part of the application inside the VM that uses shaders. This could be a game, a CAD program, or any other application that relies heavily on 3D graphics. To analyze shader usage *, the attacker needs to analyze how the application uses shaders. What types of shaders are being used: vertex shaders, pixel shaders. What data is being passed to the shaders? 3. Craft a malicious shader *, the attacker needs to craft a malicious shader that performs some harmful action. This might involve memory corruption *, the shader might attempt to write to arbitrary memory locations on the GPU. Exploitation of this might be possible, although modern GPUs have memory protection mechanisms. Exploiting driver bugs *, the shader might trigger a bug in the GPU driver itself. Leaking data *, the shader might attempt to leak sensitive data from the host system. 4. Inject the shader *, the attacker needs to find a way to inject the malicious shader into the rendering pipeline. This is the trickiest part. Possible injection methods. Modifying game files *, if the application loads shaders from files, the attacker might be able to replace the original shader files with the malicious shader. Runtime injection *, the attacker might be able to intercept D3D calls and replace the shader code at runtime. This could involve using a DLL injection technique or hooking D3D API functions. Theoretical code example, HLSL, malicious pixel shader. Explanation ***. This is a pixel shader. It's run for each pixel on the screen. UV is the texture coordinate for the current pixel. *SV_target specifies that the output of the shader is the color of the pixel. The critical part, commented out because it's purely theoretical, is the attempt to write to an arbitrary memory address, 0x12345678. This will almost certainly crash the program and / or the GPU driver. The return float for 1.0, 0.0, 0.0, 1.0 line simply sets the pixel color to red. This is so we can visually confirm that the shader is running if we manage to inject it. Theoretical code example, C++, shader injection. Explanation ***. D3D compile, * compiles the HLSL shader code into a binary shader blob. Error checking is crucial. Create pixel shader, * creates a pixel shader object from the compiled blob. Device context -ps set shader, * sets the currently active pixel shader. This is where the magic, or danger, happens. Important considerations Error handling Thorough error handling is essential. D3D API calls can fail for various reasons. Resource management You need to carefully manage D3D resources, shaders, textures, buffers. Releasing resources at the wrong time can cause crashes. Shader model the PS_5_0 string specifies the shader model. You need to choose a shader model that is supported by the GPU and the application. Hooking in a real-world scenario, you'd likely need to hook the PS set shader or other D3D API functions to intercept the original shader and replace it with your malicious shader. This requires advanced techniques. Limitations and challenges GPU memory protection Modern GPUs have memory protection mechanisms that prevent shaders from writing to arbitrary memory locations. Bypassing these protections is extremely difficult. Driver hardening GPU drivers are constantly being hardened against attacks. Exploiting driver bugs requires finding very specific vulnerabilities and carefully crafting the shader code to trigger them. remotefx isolation remotefx adds another layer of complexity. The interaction between the VM's D3D runtime and the host's GPU driver is not well documented and requires reverse engineering to understand. 5. Mitigation strategies. Keep systems up to date. Apply the latest security patches from Microsoft and your GPU vendor. These patches often address known vulnerabilities in Directx, Hyper-V, and GPU drivers. Restrict VM privileges. Run VMS with the least necessary privileges. Avoid giving VMS administrative rights unless absolutely required. Enable code integrity, HVCI. Hypervisor protected code integrity, HVCI, can help prevent malicious code from running on the Hyper-V host. GPU virtualization security. Utilize enhanced security features for GPU virtualization when available. Some GPU vendors offer features like GPU partitioning or dedicated GPU assignments to enhance isolation. Monitor VM activity. Use security monitoring tools to detect suspicious activity within VMS, such as unusual D3D API calls or attempts to access sensitive memory locations. Regular penetration testing. Regularly conduct penetration testing of your Hyper-V environment to identify potential vulnerabilities. This should include testing the remotefx vgpu configuration. Shader validation. Theoretical implement runtime shader validation, if feasible. Ideally, validate shaders before compiling them to ensure they do not contain malicious code. This is a research-intensive mitigation. 6. Ethical considerations. Legality. It is illegal to test or exploit vulnerabilities on systems you do not own or have explicit permission to test. Disclosure. If you discover a security vulnerability, responsibly disclose it to the vendor, Microsoft or the GPU vendor, so they can fix it. Impact. Be aware of the potential impact of your actions. Exploiting a vulnerability could cause significant damage to systems and data. Education. Use this knowledge to educate others about the risks and how to mitigate them. 7. Conclusion and further research. The intersection of Directx, Direct3D, and Hyper-V's remotefx vGPU represents a complex and potentially concerning attack surface. While exploiting vulnerabilities in this area is challenging, it is important to understand the potential risks and implement appropriate mitigation strategies. Areas for further research. Reverse engineering. Deep dive into the remotefx vGPU driver, both in the VM and on the host, to understand the communication protocol and identify potential vulnerabilities. Tools like IDA Pro and Ghidra are essential for this. Fuzzing. Use fuzzing techniques to generate a wide range of D3D command streams and data to test the robustness of the remotefx vGPU components. Dynamic analysis. Use debuggers and memory analysis tools to monitor the behavior of the remotefx vGPU driver while it is processing D3D commands. Shader compiler analysis. Analyze shader compilers for potential vulnerabilities where malicious shaders can be constructed that trigger unexpected compiler behavior. Remote code execution techniques. Research specific techniques for achieving remote code execution on the host system by exploiting vulnerabilities in the remotefx vGPU components. Focus on bypassing memory protection mechanisms and other security mitigations. This tutorial provides a foundation for understanding the potential attack surface related to Directx and Hyper-V's remotefx vGPU. Remember that this is a complex and evolving field, and continuous research and vigilance are essential to stay ahead of potential threats. Always prioritize ethical considerations and responsible disclosure when exploring these topics.